Yes, thanks for the introduction. So I'm Mattia Mauro. I'm a postdoc at NASA Goddard Space Flight Center and Catholic University of America, and I will be starting soon a new job in Italy and the University of Torino. So today I'm going to talk about the characteristics of the galactic center excess measured with Fermi and with 11 years of data. And before diving in the results, so the data from Fermi are analyzed using a model for the interstellar emission, point sources, an isotropic template, and if you analyze also the galactic center, it is important to add also the Fermi bubbles. And several groups analyzing this very interesting region found an excess of gamma rays, and using different source catalogs, analysis techniques, and interstellar emission models, they found that the spectrum of this galactic center excess is peaked at a few GeV. But the origin still remains a mystery, and some of the characteristics of this excess are still not clear. So in this talk, I'm going to talk about the three papers, two submitted to PRD and one under preparation. So these three papers basically follow the overview of the talk. So first, I will focus on simulations to see how Fermi can detect the characteristics of the galactic center excess. Then I'm going to analyze Fermi-LAT data and show what are the characteristics that I find with 11 years of data. And in the end, I will talk about the interpretation with dark matter and also with the cosmic rays. So the characteristics of the galactic center excess we are interested in are the energy spectrum, the spatial morphology, and if there is an energy dependence, an energy variation of the spatial morphology, and the sphericity, and so ellipticity, and the position of the galactic center excess. And I analyzed 11 years of data from Fermi using the latest source catalog and the interstellar emission model published a few years ago by the Fermi-LAT collaboration, where basically you change the source distribution, the gas maps used, and I also changed some details of the analysis in order to provide the characteristics of the galactic center excess, testing different interstellar emission models and analysis techniques. And so before showing the results with the real data, I worked on simulations, and in particular, I focused on the energy spectrum. You see in these two images, the ratio between the measured spectrum and the injected spectrum. In this case, basically, I injected in the Fermi data a galactic center excess given by dark matter. And then I analyzed the data and I try to find how Fermi reconstructs the spectrum. This is in between 100 MeV and 1 TeV of energy. And the two plots are for two different techniques. On the right, I am using a new technique that basically adds weights to pixels and for an energy range where you have a lot of counts. This serves to basically account for some uncertainty due to the mismodeling of the interstellar emission. And in fact, you see that on the right, the energy beams, the data close to 100, they have a much larger energy range. They have a much larger error on the spectrum. And using this new technique, I'm able to improve a lot the compatibility between the reconstructed signal and injected signal. And on average, basically, you have an uncertainty for the interstellar emission model that is roughly at most 10–15%. Then I analyzed the spatial morphology with two different scenarios, still with simulations. One is with the scenario where you have an imperfections of the interstellar emission model. So basically, you create the data with one model, and then you analyze the data with another model. And then the case of a missing component. So imagine that you have the data and you have the emission from one component, but then we don't know that this component exists. And so basically, we are missing a component in fitting the data. The result for the spatial distribution of the galactic center excess, and in particular in the value of gamma, that is the slope of the Navarro-Frank-White density profile, is that for an imperfection in the interstellar emission model, we expect roughly 5% of systematics in the value of gamma, and this can be seen in the left plot. On the other hand, if we are missing one component, increasing the flux of these missing components, you see that the value of gamma deviates deviates a lot from the injected signal that is 1.2. So basically, it is important to have all the components in your model, of course, and at the minimum, you expect at least 5% of systematics in the value of gamma for the reconstructed spatial distribution of the Galactic center excess. Okay, then I analyzed the data, and I'm using a baseline model with Bremsstrahlung, pi0, inverse Compton divided into the 3 different components of the interstellar radiation field. An isotropic component, I model the extragalactic emission, and then the sun, the moon, loop 1, and then the Fermi bubbles divided into a low and high latitude components. Now, fitting the data, I find residuals that are roughly 20–25% of the data, and this is more or less the same level of residuals found also in previous papers. So you see in these 2 images, on the left, the residual I find, on the right, the one found by the previous Fermi-LAT paper on this topic, and the residuals are at the same level, basically 20–25% of the data. Okay, so the first characteristic I analyze in the real data is the energy spectrum of the Galactic center excess. And here you see 3 different plots on the top left, top right, and bottom left, the spectrum found by using different interstellar emission models created from different source distribution, gas maps, or different analysis techniques. And on the top right, you see the comparison between the envelope of all these results I find with the black data and band in comparison with the previous analysis, a few previous analyses, Calor et al. And Ackermann et al. So you see that the band I find is comparable with the one of Calor et al. 2014 and is much smaller than the previous Fermi-LAT paper, because I'm not including in this band some of the models used in Ackermann, where they included some emission that can be very degenerate with the Galactic center excess. But roughly, the spectrum is compatible with previous analysis, so it's compatible with the log parabola and with the peak at a few GeV of energy and the high and low energy tail. The second quantity I would like to quantify is the spatial distribution of the Galactic center excess. And so the technique I used is independent from the particular dark matter spatial template. So I include in the model concentric rings, and I test a different size for these rings, and then I fit the rings to the data. After the fit, I find the surface brightness of each ring. And in this way, basically, you have a model independent in the sense of the dark matter template, a model independent surface brightness data that I can use to fit the data and find what is the spatial morphology of the Galactic center excess. In these 4 plots, you have the data for the surface brightness in 4 different energy beams from 1 to 10 GeV, with the best fit with Navarro-Franke-White, where the best fit value for the gamma index is between 1.2 and 1.3. So now we can see if there is any variation of the value of gamma as a function of energy, and this is what I'm showing in this slide. So each plot is the value of gamma as a function of energy for different choices of the interstellar emission model and different choices of the analysis technique or data selection. On average, the conclusion is that gamma seems to be pretty constant as a function of energy. There is no large or systematic variation with energy, and gamma is roughly between 1.2 and 1.3. So the spatial morphology of the Galactic center excess seems to be pretty constant as a function of energy. And there is a variation with the different interstellar emission model or analysis techniques that is roughly similar to what I found with the simulation. So basically roughly 5–10%. Then I try to find what is the position of the Galactic center excess, basically running a likelihood analysis where I move the position of the galactic center excess template using a dark matter template with gamma equal to 1.25. And in these plots, you see the delta log likelihood between the best fit position and all the different log likelihoods of the other pixels. And the best fit position is roughly compatible with the dynamical center, dynamical position of the galaxy. And so this is something that we expect, for example, if the galactic center excess is due to dark matter. And you see in this slide that the range of longitude and latitudes using the different interstellar emission models and analysis techniques. Then we tested the sphericity of the galactic center excess because recently Mattia and collaborators since 2018 pointed out that using for the galactic center excess an interpretation that is due to pulsars located in the galactic bulge and using also nuclear bulge, basically you can fit very well the data, and in particular better than what you would do if you use a dark matter template. And these templates are not spherically symmetric, and so testing the sphericity of the galactic center excess is important to see and to disentangle the interpretation for this excess. And so what I do is to modify the dark matter template, making it elliptical and changing the ratio between the axes between 0.4 and 2.2. And the best fit value for the ratio of the axis and for the value of gamma can be seen for 3 particular models in the bottom plots. And so basically the ratio is between 0.8 and 1.2 and gamma exactly as we found before. So the galactic center excess actually seems to be roughly spherically symmetric. And I also tested the models by Mattia et al. 2018, and what I find is that using the nuclear bulge and the boxy bulge or the nuclear bulge and dark matter, basically the inclusion of dark matter actually improves the fit. So my results are actually somehow different from what they find, and this needs to be investigated more in the future. Okay, now for the interpretation, the first interpretation I investigate is the cosmic ray electrons injected from the galactic center with the sunburst happened millions of years ago. This one was an interpretation used and published by several papers. The problem of this interpretation is that the signal will have a spatial distribution that is energy dependent. This can be seen in the plot in the left, where you have the data I found before with the real data. So all the color data are from previous results, and the black stars are using a simulation with cosmic ray electrons. So you see that the gamma value with cosmic ray electrons injected from the galactic center would have a gamma that increases with energy, and this is expected because of more energy losses for high energy electrons with respect to low energy electrons. And there are no there is no interstellar emission model that shows this systematic increase in the value of gamma. And on the right, in addition, it is difficult to fit the inner few degrees of the surface brightness with this interpretation, because the surface brightness from cosmic ray electrons, it is too flat. So probably you need an interstellar radiation field that increases a lot in the galactic center. And it is also challenging to fit the galactic center excess spectrum.
2 minutes.
Yeah, see, yeah, I'm perfectly in time. So the cosmic ray protons is an alternative. The problem of this interpretation is that the signal, as you can see in the left, this is a simulation from cosmic ray protons that produce gamma rays from pi zero decay. You see that basically you need gas, interstellar gas, to produce gamma rays from cosmic ray protons. And the interstellar gas is expected to be elongated on the galactic plane. And so the spatial distribution is not spherically symmetric as seen from the data. So the dark matter interpretation fits very well. As you can see in the top left, the data, the best fit for dark matter is given by the blue dashed line with the index of 1.27. by construction, the spatial morphology will be energy independent. And you can fit very well the spectrum using, for example, a BB bar channel with 40, 50 GeV and a cross-section that is close to the thermal cross-section. And this signal is still not completely ruled out by other searches in gamma rays, for example, dwarf spheroidal galaxies. The final interpretation could be millisecond pulsar or young pulsars located in the galactic bulge, and in particular with this is motivated by the latest result by Mattia et al. 2018. But there is still some discussion in the community, also given the latest result by Bartels and Lee. So this needs to be investigated a lot more in the future. So to conclude with simulations, I found what is the sensitivity of the LAT to find the characteristics of the galactic center excess. Then I applied the analysis to 11 years of data, and I found that the morphology is compatible with a Navarro-Franken-White dark matter density profile with gamma equal to 1.25. There is a systematic uncertainty of 60% in the spectrum at a few GeV, and the galactic center excess seems to be roughly spherically symmetric and with a spatial distribution that does not change with energy. For the interpretations, for sure, there is still a lot of work to do in the community. There are some interpretations that seems to be disfavored unless you really change our idea of the interstellar medium density and spectrum in the galactic center, and some others seems to be viable, for example, dark matter or pulsars, and we need to do a lot in the future to confirm or not some of these interpretations. Okay, stop here and I take questions.
Great, thank you very much. So our first question is from Ned Wright, who asked, does your inverse Compton model include the effects of the anisotropic radiation field?
No, this model is not including anisotropy of the interstellar radiation fields. This is basically is following the interstellar radiation field from Galprop, and is using the distribution and the energy spectrum from this model to create inverse Compton.
Great. Our next question is from Manel Arando, who asks, besides having a few more years of data, is the data weighting method the only substantial difference between your analysis and previous ones? And can you explain a bit why the weighting would give a more robust analysis?
So the weighting is one of the improvements. The other improvement is a systematic search of an energy dependence of the spatial morphology. This was not investigated with such details as I do in the past. And this is very important because, as I have explained, some of the interpretations can be ruled out if there is no evolution with the energy of the spatial morphology. The weighted likelihood technique is a way to basically include the systematics on the interstellar emission model in the analysis, basically by deweighting the pixel for which you have a lot of counts. And so if you look to the maps, you see that, for example, at close to 100 MeV, the weights are very, very low. So these energies are deweighted because at 100 MeV, you have so many counts. And so the interstellar emission model is so bright that some systematics in this component are very large with respect to higher energy, for example, above 1 GeV, where the weights are closer to 1.
Great, thank you. Pranab Ghosh asks, does the inferred gamma value put constraints on the nature of dark matter?
Yes, it does. And this value of 1.2, 1.3 is pretty compatible with what we expect in the Milky Way and what we find from numerical simulations.
Great. And our last question from Christine Yi asks, can you speak on possible interpretations of the centroid location?
Okay, so the centroid location, if the centroid location will be not compatible with the dynamical center of galaxy, this implies that probably dark matter is not available interpretation, because from numerical simulation we expect that for gravity the center of the highest peak of the density is in the dynamical center of the galaxy. While on the other hand, all the other interpretations are probably viable. So yeah, the position of the centroid with respect to the dynamical center of the galaxy is very important to disentangle the interpretation.